4 light-years away, a rocky world called Proxima Centauri b orbits its host star. We know its mass, its temperature, and its orbital period, despite the fact that no human or telescope has ever actually seen it. For most of human history, planet hunting was a direct visual observation. Mercury, Venus, Mars, Jupiter, and Saturn were simply the bright points of light that moved relative to the fixed background of the night sky. As telescopes grew larger, astronomers used mathematical anomalies in orbits to point their lenses at specific coordinates, revealing the distant, icy giants Uranus and Neptune. But modern exoplanet discovery faces a physical barrier that lenses cannot overcome through magnification alone. The stars these planets orbit are millions of times brighter than the small, dark worlds circling them. To a telescope, that planet's light is indistinguishable from the star's glare. It is like trying to spot a single, tiny firefly positioned directly in front of a massive stadium searchlight. To find these worlds, astronomers have shifted away from direct sight, looking instead for the physical signatures a planet leaves on the light of its host star. The most common detection method is the transit method. It occurs when a planet passes directly between its host star and our vantage point. As a planet crosses the star's face, it blocks a tiny fraction of light. Telescopes measure this rhythmic dip in brightness. Finding these dips on a repeated schedule allows scientists to calculate the planet's size and speed. Because other cosmic events can cause dimming, every signal must be tested against alternative explanations to confirm a planet is actually present. This technique has been the primary tool for dedicated space missions like Kepler and TESS, which have identified thousands of worlds by monitoring the steady light of distant stars. By analyzing the depth and duration of these shadows, researchers build a profile of a world they cannot visually resolve. However, the transit method only works if the planet's orbit is perfectly aligned with Earth. If the system is tilted, we need a different way to measure the planet's influence. This is where radial velocity comes in. Even though the star is far more massive, a planet's gravity exerts a small but physical tug on its host, causing the star to move in a tiny orbit of its own. It wobbles. We detect this motion through the Doppler effect. As the star wobbles toward Earth, its light waves compress, creating a subtle blue shift. As it pulls away from us, those waves stretch out, resulting in a redshift. A related technique, astrometry, tracks this exact same physical movement by measuring the star's precise coordinates on the sky over time. A heavier planet pulls harder on its star. Measuring the intensity of this wobble allows scientists to determine the exact mass of the orbiting world. Some methods rely on the way mass interacts with space-time itself, utilizing theories first proposed by Albert Einstein. In gravitational microlensing, the gravity of a foreground star acts as a cosmic magnifying glass, bending the light of a more distant star behind it. If that foreground star has a planet, that planet adds its own gravitational weight to the lens, causing a distinct secondary spike in the magnification. To actually see light from a planet, telescopes use coronagraphs, internal masks that physically block the blinding glare of the host star, revealing the faint photons reflecting off its outer planets. Whether they are measuring the bending of spacetime or physically masking a star's light, these techniques allow astronomers to bypass the limitations of traditional observation. When researchers confirm the existence of a world like Proxima Centauri b, they are presenting the result of high-precision physical measurements. They cross-reference Chardo timings, starlight frequency shifts, and distant light magnification. Combining these data points provides the planet's mass, its orbital distance, and in some cases, the chemical composition of its atmosphere. The discovery of new worlds has evolved into a discipline of correlating indirect signals across years of observation. We map the galaxy by interpreting the subtle gravitational and electromagnetic interactions that stars broadcast across the void of space.